We're going to solve some inequalities with rational functions. We're going to start with the rational function given to us in A, and here we are being asked to find where the function is greater than 0. In other words, where it is positive, i.e. where it is above the x-axis. So all those things are going to help us kind of inform our process that we go through. And when we think about finding where the function is positive, we kind of realize, oh look, we already do this when we're graphing the function, when we create a sign chart and sort of go through each segment and say, okay, is it going to be positive in this region or negative? And we know then that it will be positive or negative for that whole region. And so we're going to go through that process here. And to create our sign chart, right, the idea behind a sign chart is to identify all the critical points, the critical values of our function, either where it will hit the x-axis, where its roots are, or where it is undefined, and then we know that between all those points, it's either going to be positive the whole time or negative the whole time, because we found all the roots, and so then we know, hey look, if I find some value in between that's positive, it will always be positive in that region. So we're going to go through and we're going to find those critical points. And the first critical point that we're looking for, and maybe I'll skip this for a second. The first type of critical point that we're looking for is where the function is undefined. And that is, of course, where our denominator is going to be equivalent to 0. So where will 4.9x squared minus 3.1x plus 10 equals 0, and here we want to use the quadratic formula to solve for x, so x will be equal to, and you want to go ahead and do that on your own and then check your answer here. Hopefully you notice that the roots that you get are in fact complex numbers, and you want to think briefly about what that means about the denominator of your function. If it has complex roots, well, are there any real values which will allow your quadratic function to be equal to 0? And the answer is no, there are no real values. You can't graph those values on the real number line. So because these are complex roots, we have no places where our function is undefined. So that's easy. Next we want to find our roots. So this would be where it's undefined. And now we want to find the roots of our function, and that's going to be when the numerator is 0, or when 3.7x minus 2 is equal to 0. And you can actually kind of think about doing this in your head, right? You can add 2 to both sides and then divide by 3.7. 3.7 is very close to 4, so 2 over 4, it's going to be about 0.5. In fact, x is equal to about 0.54. And so that's your only root, right? There's no other place where the function is gonna hit the x-axis. So when you use this solo point as your critical value, and here's the great thing, you know that the only place that hits the x-axis is right there. So to the left and to the right are going to be the only places you need to check. So if you plug in 0 on the left side there, you'll notice you're going to get a negative on top, and on the bottom here you should note that this never hits the x-axis, so it's either completely positive or completely negative. And you know, since it opens upward, it's got a positive coefficient, that it must be completely positive. There's no way that it could open upward and be completely negative. So this is always going to be positive. So to the left it's going to be negative, and to the right we are going to be positive. You can think about it, if you plugged in positive 1 here for x, you get a positive value in your numerator. So where is your function going to be greater than 0? Well, that's going to be every value to the right of 0.54. So for A, it is when x is greater than 0.54. Moving on to B here, we want to follow that same path, right? We want to find the critical values, and we want to use those critical values to create a sign chart where we can kind of segment the portions of our function which are going to be important for us to test, and then use those. So similarly, where is my function undefined? That's going to be when x is equal to -2. And what are the roots of my function? So this is when 3x squared minus 20 is equal to 0. And now I could use the quadratic formula. I encourage you to do that if that's the way you are most comfortable, but I can also solve this since there's no x to the first power term. I can solve this pretty quickly, and I'm going to end up getting x is equivalent to plus or minus. Now remember, we're going to have 20 divided by 3. That's about 7, right? So we'll call it 6.9. It's going to be plus or minus the square root of 6.9. What is that? We can simplify it. The square root of 6.9, right? 6.9 is in between 4 and 9 somewhere. So we know the square root is going to be in between 2 and 3. 6.9 is slightly closer to 9 than it is to 4. So, why don't we call it 2.5 or so? But I encourage you to actually go on your calculator and find that value because you're going to want to, be as accurate as possible. So we'll call it about 2.5, and that's plus or minus, right? We have two possible roots because this is a squared function, right? So when I square root it, I'm thinking, hey, no matter whether I plug in positive 2.5 and I square it, I'll still get a positive value. Or if I plug in negative 2.5 and I square it, still going to get a positive value. So either one will work there. And so this gives me all the different values I need. I have negative 2.5, I have negative 2, and then I have positive 2.5. And then you just want to go through and test all those different points. So I encourage you to do that now. Go ahead and then write out your intervals where your function is going to be less than or equal to 0. So if you go through and you check, you will find that it is negative to the left of negative 2.5. It is positive on the next interval. It then moves to negative and then positive. So we want to kind of take this in two steps, right? We want to know where our function is less than or equal to 0. So let's just start with the less than 0. Where is our function negative? And then we can kind of add on to that if need be. So where is the function negative? Well, it's less than 0 everywhere to the left of negative 2.5. So when x is less than 2.5, I'm sorry, negative 2.5. And it's also negative when x is either greater than negative 2 or less than positive 2.5. And that's pretty easy to see. But now we want to include the places where the function is actually equivalent to 0 because we want to know when it's less than or equal to 0. And those are at the two roots, right? When x is negative 2.5 or when it is positive 2.5. And so we will include those by making all those less than signs, less than or equal to.